of my talk to present some first results from the MUD project. And I confess it's a little bit cheating in the sense that, as you will see, the MUD project has just started. So I will give you a few preliminary, fresh from the oven results. But actually what I want to do in this talk is to put really the star-forming disks under the spotlight and to make the point that understanding how disks grow their stellar mass at any radius, at any time, in any environment is really at the core of understanding the evolution and growth of the entire galaxy population. So what I will do is actually to present a few results new since last year, and then present you MUD and what MUD wants to achieve. So the start of the story is indeed the star-forming main sequence across cosmic time. That speaks for a correlation between the star formation rate and the mass, almost 1-to-1. And in particular, also to put it together with the fact of how the star-forming population grows with time. These are the mass functions from the Hilbert paper that you see here, starting redshift 4 and accumulating. And pointing out that at least up to where one has been able to study the structure of these star-forming galaxies, it seems that the bulk of the population is made by disks. Of one sort or another, more complex maybe than in terms of structure or different than what we see locally, but certainly disks. One striking thing of these mass functions that we must keep in mind, it has already been highlighted in this workshop before, is that if you look at the M star of the mass functions through cosmic time, this is unbelievably constant since redshift 4 in the very least. And I think it's even more striking that the same M star is true for the quenched galaxies. So M star is a pretty much boring number in this universe as galaxies grow, and these might be telling us something. And so this is my ansatz. What they may be telling us is that actually we populate this M star bin of the quenched spheroids coming straight down from the star-forming main sequence without doing much more than this, quenching them somehow, and we will, of course, we will be discussing this more how. So this is a little bit the question I want to raise. Do M star quenched spheroid just fall down straight for quenching from this sequence to here, based in the very least on these and many other indications that these actually may be a sensible ansatz. So before I continue, I want to show one slide that I showed last year, but I do want to remind everybody that when we come to the redshift 0 spheroidal population, the M star, the 10 to the 11-ish mass value is actually a pretty dramatic watershed, because if you go above the M star, when you start looking at very gigantic, above 10 to the 11 solar masses spheroids, you have objects that we can study in detail, and so we know that they are the slow rotators, they have the famous 100 parsecs cores in the centers, they have boxy isopods, they have flat gradients. By the way, they are the oldest in the universe. And so all this says that they have been seeing their last phases of growth in a dissipationless way. And indeed, I don't think there is any other way that we can make those objects, if not by some form of dry mergers, which, by the way, could be major mergers, or could be the famous minor accretions around the very dense cores, which are made very early on in the universe. As we come instead on this side of the watershed, we're seeing objects which are fast rotator, cuspy in the centers, disky isopods, steep metallicity gradients. These objects have had a very dissipatory formation. And indeed, there is no way to make all these properties we see if not through gas-rich physics. So the disclaimer is that as I continue discussing, please don't think of the side of the mass bin. Think of this side, think of the M star bin, where I am sort of trying to see whether we can shoot down galaxies from the star-forming main sequence, to the quenched population of spheroids. Okay, so is there evidence for this? And I believe, yes, there is. And in particular, let me remind you again, I showed it to you last year, that if we look at M star, there is no doubt that as time evolves, where you're adding the new quenched spheroids with cosmic time. This is a ratio of number densities between redshift 0.2 and redshift 1, is at the large sizes. So we are creating, as time goes on, larger and larger quenched spheroids. And of course, this could be a conveyor belt in which you keep making attempt star compact objects and you accrete stuff around them. But if you look at the ages, stellar ages of these objects, here Portman approach in a rest frame U minus V color as redshift goes from here to lower redshift, and you compare the ages of the large population and of the small population at each in each bin of redshift, the larger objects are always younger than the more compact objects at the same mass at the same redshift, and also because they are bluer than the compact objects. And so actually this also supports that at any epoch, if this idea is correct, you get the larger spheroids because you quench larger disks, which is completely consistent with this aging of the compact of the spheroids at M stars. Yesterday you heard Mauro showing that indeed the compact objects up to redshift 1.3 or whatever are younger at the same mass than their more extended siblings. It's what I was showing to you from my 2013 paper with the colors, and now instead here again is the same as Mauro did with the spectra from the Z Cosmos spectra, confirming precisely the same result Mauro showed to you, the same I showed to you with the colors, now with absorption features. If you take at any redshift the compact population at a given M star and you compare it with the larger population, the compact population is older than the larger population. So this really is supportive, I think, in an indirect way, of course, of the fact that we are taking the star-forming M-star disks and we are shooting them down into the pile of the dead and red quenched spheroids at M-star. Is this the only evidence we know? Very quickly, no. There is actually much more direct evidence. With my student Sandro Tacchella in Zurich, what we did was to use data from the SINF project that Reinhard has been talking about yesterday. The point is that we have adaptive optics symphony spectroscopy of H-alpha for this object, so we can actually resolve at the same resolution of HST the star formation at 1 kiloparsec scales inside these redshift 2 galaxies in particular. And let me firstly say that the bottom line of this plot here is that if you compare the stellar mass densities at different masses with the star formation rate density profile, so the stellar mass is always more centrally concentrated at redshift 2 in this star forming. I should have said these are star forming disks on the main sequence at redshift 2. So the stellar mass is always more centrally concentrated, and if you look at the specific star formation rate profile through the body of the galaxy, it's always increasing. So these galaxies have already quenched cores, and when you go then to a quantitative comparison with the stellar density of stars, with the stellar mass density in these objects, when you come here to the sort of M-starish regime, the stellar mass densities have already saturated at the stellar mass densities that we find in the M-star spheroids in the local universe. So there is not much more room for the inside stellar mass density to grow, because they cannot go above what has already, what we see at redshift 0. And again, I think this is direct evidence in some way that what's going on is that we are making up a little bit of star formation in the outskirts and leaving the dense cores already made to what we observe in the M-star spheroids at redshift 0. We could actually play, because we did have the star formation rate profiles distributions across the disk at this 1 kiloparsec resolution. We could play a simple model in which we do take our observed star formation rate profiles through the objects and see what evolving them down to lower redshifts following the observed profile keeping the galaxies always on the main sequence. And what do we find in this sort of modeling is that, yeah, the inner cores will quench very fast on a few 100 million year time scales. In the outskirts, it's going to take over a couple of billion years to complete the star formation or using this outskirts, this gas in the outskirts. How much mass do we add? Of order 10 to 15% of the total object. And this means that essentially, indeed, if we just take these star-forming disks on the star-forming main sequence at redshift 2 at M star, and we just let them do this evolution, exhausting the gas that they have inside on these large extended disks that Reynard has shown, we will, at some point, exhaust their fuel and will bring them down to the population of M-star spheroids, which preserve this stellar densities already made and indeed have the properties that I already highlighted. So is this sort of conceptually sensible? Well, completely conceptually, starting from the smallest number of assumptions you can and the simplest also that you can. Let's see whether if we build disks through cosmic time in the universe just according to disks growing in terms of size and mass as the halo do, and just using the specific star formation rate evolution in the universe that we actually observe, let's see what we get if we end up quenching them once they grow in this way in size and in stellar mass, with a mass proportion, with a probability to be quenched just by reaching a certain mass statistically, as we had proposed in the Peng et al. 2010 paper, which I think many of you are familiar with. So here there is just growing disks according to the relationship of growth of 10 left. Wunderbar. Okay, so I can relax. Okay, so what happens? What happens is a number of stamp plots that I have on the slide, which by no means I want to go one by one, but I put them there because if anybody wants to ask, do you get the surface mass densities? Yeah, I can show you the plot. Do you make the transition in surface mass density which has been observed through cosmic time? Yes, I can show it to you that we do. Do we get the mass size evolution? Yes, we do. And so on and so forth. One thing that I want to emphasize is that one thing we must be cautious when we interpret what quenches, how quenches happen, is to reflect that we have a problem in the observations of sort of not knowing what's cause and what's effect. I'm not saying that this is how the universe evolves, but I'm saying that this is how, very simply, disks very likely grow. And if they grow like this, for example, you end up quenching with an algorithm which is only proportional to total stellar mass, has nothing to do with the surface mass density, and yet you do get precisely the surface mass density evolution that we observe. So in this case, the galaxies don't quench because they have a certain surface mass density. They quench, and if they happen to have that surface mass density. So surface mass density becomes an effect and not a cause of the quenching. So, of course, we don't get from simple approach models like the one I have explained in three very simple equations what's going on and what's the physics that we are observing. And for this, indeed, we must go to the simulations. And what I'm showing here is the distance from the main sequence as time as a function of mass. And I will show you a little plot that shows us from the simulations what goes on inside the main sequence. The simulations are Daniel's simulations, and this is work that Sandro Tacchella has done in particular together with Avishai. And Avishai has given you a long and detailed version of what we see. I give you just the cartoon because in the context of what I'm telling you, what I want to emphasize is that indeed, as we try to understand the physics of how the disks grow on the main sequence, we do see inside the computer these oscillations that pass through phases of compaction when the gas drags everything in the core and more extension that mean these oscillations around up and down the edges of the observed main sequence. And indeed, I want to reemphasize what Avishai nicely described for us today, this quenching attempts as the galaxy gets here. And then because the conditions of the timescales between replenishment and depletion are just not right, because the masses of the halos in which these objects find themselves are not yet good enough to sustain this virial shock, the objects can't quench, and only when this condition is reached, the object goes down. One thing that I think Avishai hasn't emphasized this morning, which I personally, I love to discuss more with you, Avishai, in first place, and with everybody else, is that I understand from Sandra and Avishai that these oscillations that we see up and down the main sequence actually happen on a fraction of the age of the universe at any time. So this very naturally tells us that if the galaxy finds itself on the star-forming main sequence at redshift 4, it's going to do these oscillations on something like a few 100 million years. If, of course, the galaxy finds itself on the main sequence today, it's oscillating with up to 8 billion year time scales. And just this natural fact that the universe ages like the rest of us just explains a lot of what we are actually seeing in terms of the spheroidal population today. So, it seems to me that we can understand a lot of the galaxy population if we just understand the disks. And then this is the time when I switch and say, but do we understand the disks, despite the fact that I spent 2 slides and several minutes trying to tell you that both from a very simple analytical perspective and from the simulation perspective, we're getting to the point of starting really scratching what the universe is doing. And from now on, I actually want to go back to the other side. I want to go to the side that reductionism is wonderful, but we may be missing a lot of important facts if we reduction too much and we don't remember the complexity that actually galaxies are showing to us. And I want to go back to early work that I myself and many other people, of course, were doing in the late 90s when we were looking at these galaxies with HST and being totally bewildered by the complexity of structure that these objects show. And this complexity at redshift 0 may teach us a lot about redshift 0 universe, but also may be a way to keep understanding how the universe evolves early on and makes the galaxy population that we are inheriting today. Let me just remind you keywords that they are absolutely perfectly exponential disks in which you go with HST down to 5 parsecs and you just find a simple exponential. Then you go to another object, and these are only 30%, by the way, because any other disk, for example, even if you don't see a distinct component, when you look at it, it's actually over dense relative to an exponential. And this even without bothering with objects which seem to have a distinct component. We have been calling them bulges, pseudo-bulges, without the fact that we have been seeing nuclear star clusters which overlap in mass with the actually bulges, but they are much more dense and compact than the bulges that we see. And again, all this is just the surface of the mass, because then all this coexists with what we call the classical bulges. All populations can be young, can be old. They are the nuclear star clusters in the very center of the disks, where actually, of the exponential disk, where you don't know how they got there, because how can you know where the center is if there is no indication that there is a sort of structure in the potential. And instead, you have a wonderfully sort of steep potential, at least judging from the stellar density, and yet the star cluster decides not to be in the center. I know I'm going into folklore, but the point I want to make is there is a lot of important information that we would like to understand a little bit better. And this structure, this information that we know is there and we're underusing, actually may be hiding answers to what I think are extremely important questions. Is this formation different at redshift 4 than at redshift 0? So are, for example, these different densities in the disks a relic of the fact that some are made earlier and some are made later? And so on. Mark has already shown his hand with less than 5, 2 at this point. So all obviously, I don't need to tell you which important questions we have opened. The point is that there are these important questions. And I think now we are moving into a situation with extensive data sets and gorgeous data sets where we can start acquiring a lot more information, because we are going to get for the disk population the two-dimensional chemical and dynamical masses, which we haven't been seeing so far. However, I do think that these actually surveys are gorgeous. They're going to give us the statistics of the population, but they're not going to give us information on how stars and gas interact on the scales there where feedback becomes important, which are the very much smaller scales below certainly 100 kiloparsecs. And all the other issues that I will show, that I was sort of raising without reading, they do need us to look at the disks on resolutions which are substantially smaller than 100 parsec. And this is now where the math project starts, and the last couple of minutes only. I just want to advertise math because we just started it. It's a large program on the VLT with MUSE, the integral field spectrograph which we just mounted. This is just a nice picture, and this is how it looks like. It's a lot of wires. Let me just say that MAD stands for the MUSE Atlas of Disks. I do need to wrap up, but essentially get that we are going to observe over 100 galaxies with MUSE over the next 3 years or so, or 4. And in particular, we are going to trace the star-forming main sequence at redshift 0. This is so a statistically representative sample, not just a few NGC numbers. Important players, I want to highlight that people like Joanna here in the audience, and Sandro Tacchella and Masato Nodera have already worked a lot for this project. The team is, of course, much bigger with the GTO. We are basing it on the HST archive. We will be applying for ultraviolet data for these objects. And I can tell you much more if you want. Let me just say that the program started acquiring data in April. So what you're seeing, those beautiful maps, for example, for the gas component for just one galaxy to show you the magnificence of the MUSE data, is just what we have been doing on the 10 galaxies we already observed since April. And by the end of this year, we should have a sample of order 25 or so. Same things we do, of course, with the stellar components. Again, I love to, for whoever has tried, I did try to do absorption lines in the star-forming galaxies with Sauron and with other things, and I gave up. The MUSE data are simply unbelievably beautiful. My last slide is the famous results, and Mark is killing me. I promise So, for example, this is how you see the emission line ratios. So what do they mean when we do the averages not only over entire galaxies, but over kiloparsec patches? Metal-rich gas present at all radii, and the metallicity gradients being due only to high star formation.
It could be worse. I've seen Mike Norman give bear hugs.
High star formation rate regions. Specific star formation rate density, a second parameter in the stellar mass metallicity relation. So a local version of what we see integrated over the galaxies. And here is my summary. And the most important thing is that because I think galaxy formation up to M star is nothing else than disk formation, we will be working at redshift 0 together with the rest of you will be working on it too, and not I redshift, and I think the future is fun. Thank you.
One question.
A good one.
One question from someone, anyone.
Oh.
Everyone's overwhelmed. All right.
Okay.
Yes, Joanna, please set up. She could give Avishai lessons.
So one quick question then. You listed all of these concerns you have with disk formation, sort of but and they're all trouble. But which one is sort of, in your opinion, the one that's most troubling?
Well, then the summary. We heard from simulations yesterday, people saying that they were realistic, and then I learned that realistic doesn't mean right. And we are missing the constraints of what stars with feedback is, and until we look on scales where this makes sense, and we give constraints that people can go and use, we will have this discussion. So we hope to contribute to clarifying, for example, this discussion. Okay. Of these mass functions that we must keep in mind, it has already been highlighted in this workshop before, is that if you look at the m star of the mass functions through cosmic time, this is unbelievably constant since redshift 4 in the very least. And I think it's even more striking that the same m star is true for the quenched galaxies. So m star is a pretty much boring number in this universe as galaxies grow, and these might be telling us something. And so this is my ansatz. What they may be telling us is that actually we populate this m star being of the quenched spheroids coming straight down from the star-forming main sequence without doing much more than this, quenching them somehow, and we will, of course, we will be discussing this more how. So this is a little bit the question I want to raise. Do m star quenched spheroid just fall down straight for quenching from this sequence to here, based in the very least on these and many other indications that these actually may be a sensible ansatz. So before I continue, I want to show one slide that I showed last year, but I do want to remind everybody that when we come to the redshift 0 spheroidal population, the m star, the 10 to the 11-ish mass value is actually a pretty dramatic watershed, because if you go above the m star, when you start looking at very gigantic, above 10 to the 11 solar masses spheroids, you have objects that we can study in detail, and so we know that they are the slow rotators, they have the famous 100 parsecs cores in the centers, they have boxy isopods, they have flat gradients. By the way, they are the oldest in the universe. And so all this says that they have been seeing their last phases of growth in a dissipationless way. And indeed, I don't think there is any other way that we can make those objects, if not by some form of dry mergers, which, by the way, could be major mergers, or could be the famous minor accretions around the very dense cores, which are made very early on in the universe. As we come instead on this side of the watershed, we're seeing objects which are fast rotator, cuspy in the centers, disky eyes. The title of my talk to present some first results from the MAT project. And I confess it's a little bit cheating in the sense that, as you will see, the MAT project has just started. So I will give you a few preliminary, fresh from the oven results. But actually what I want to do in this talk is to put really the star-forming disks under the spotlight, and to make the point that understanding how disks grow their stellar mass at any radius, at any time, in any environment, is really at the core of understanding the evolution and growth of the entire galaxy population. So what I will do is actually to present a few results new from since last year, and then present you MAD and what MAD wants to achieve. So the start of the story is indeed the star-forming main sequence across cosmic time. That speaks for a correlation between the star formation rate and the mass, almost 1-to-1. And in particular, also to put it together with the fact of how the star-forming population grows with time. These are the mass functions from the Hilbert paper that you see here, starting redshift 4 and accumulating. And pointing out that at least up to where one has been able to study the structure of these star-forming galaxies, it seems that the bulk of the population is made by disks. Of one sort or another, more complex maybe than in terms of structure, or different than what we see locally, but certainly disks. One striking thing